established laws of mechanics we use, laws, so we'll go back and study their origins. Thermodynamics is all about energy. And we've already discussed this for the last time. Making some characteristics of energy, mainly its capacity to do work, W, and or drive a heat flow. Heat flow we call Q. Dimensions of energy are mass, length squared, inverse time squared, which are just right there in our memory. Anything with these dimensions is probably a form of energy or closely related to it. What are the forms of energy? Well, we saw all about those last lecture. Review some of that. Here we have this classification I put down that lists all the forms of energy that I have any familiarity with, except one that was missing. And what was that?
Light.
Of course, light. And that came out in the period. I may have asked, does it belong in the classification? The answer is yes. Light's energy. Radiation's energy. Is there a place here for it? The answer is yes. Can I tell you about that? The answer is no, because I don't have time. It's not a part of this part of the study of physical chemistry. Part of the study of physical chemistry, not this part. But I did offer some things to think about. We're all taught that light is a wave and light is a particle, and that it's the same the whole time. And if you grew up comfortable with that feeling in your gut, and yeah, I understand about light, it's one of these funny things, it's a particle, it's a wave. Then you'll understand that. And you have to understand that there's no difference in our knocking the frog off the lily pad with the rock and disturbing him by creating a wave that goes out and disturbs him. I don't know how to throw one rock and knock 6 or 7 frogs off the lily pad scattered around Lake Alice, but one big splash would affect all of them in time because the waves will walk out and fly. If you think they're the same, then you're just feeding yourself a empty jar. Now the story of how this dilemma arrived, and the story of how it was resolved is perhaps the most glorious story in the study of physical science. Because it's aggravated, I can't tell you about it. So I can't talk to you about that now, because it takes a while. It's worth the journey. I still say water's missing. A couple other things we haven't mentioned. Anybody have any idea what? Well, what was the first or second thing I said here today about thermodynamics, study of energy, and modern characteristics of energy? Capacity to do work, capacity to drive heat flow. There is 2 things. Where does heat belong? Heat form of energy? I see. We'll talk about heat. We have to. It's thermodynamics. Heat and motion. Where does heat belong here? If energy is capacity to drive heat flow and to do work, where does the work belong here? Well, where I cannot tell you about how light belongs, where it belongs, and how the apparent confusions about dual nature really are requisite. We can explain everything we know about science without having to burden ourselves with that particular view. And the reason that we continually do has to do with the fact that science is not what it can be or should be, it's what it is. And it's a creation of human beings. And it suffers from all of the remedies of that condition. And one of them is just boundless arrogance of our species, especially big-time scientists. So, I can't tell you about life, but I can tell you something about heat and work, and that's in our syllabus, and so we're entitled to pursue this. So, some facts that you should know about energy, heat, and work. And I'll just run through these one at a time. This will all be posted this afternoon in highly legible form, except for the handwriting there. So just pay attention now and then review it later. So the flow of energy across the system boundary due to temperature difference between the system trying is heat. That is heat. Someone asks you what's heat, that's it. Can you say it other ways? Yeah, but that's it. Nothing else is heat. Nothing else. The flow of energy across a boundary driven by a temperature difference. I can't make it any simpler than that. Any other flow of energy across the system, anything else that involves energy transfer is called work. Energy, we use U for that, for some silly reason, is a state property of matter. So its derivative is exact. When it changes state of any system, delta U is the integral of du, and it depends only on the final energy and the initial energy. Where you start, where you stop, it makes a difference how you go there. Infinitude of ways go from A to B. The change in energy depends only on A and B. That is so glorious. And that's true for all state functions in thermodynamics. And that can really solve our problems and eliminate our headaches. Heat and work, on the other hand, are not forms of energy or properties of matter. They are descriptions of energy flows. If the system's energy changes, then energy U must cross the boundary. The system experiences change in energy, and some energy has to come in and go out. And the transfer of energy can occur only as a form of heat, or a work effect, or a combination of two. That's it. The only way is that system can have a change in energy. All right, there's some facts we need to know about. I elaborate on that just a little teeny bit here on this next page, which I also will post. So here's a little diagram. Hope you can see it.
There you
But, showing a system, I generally draw a circle or a crude loop around something, we name it a system. Undergoing a change in state 1 to state 2, and some energy crossing boundary can go by a heat path flow or a work path flow. We know either direction. So that sums up the first law again. Change in energy of the system is heat flow to it plus work down. du, dq plus dw. Heat flow to the system, work done on the system. That's another statement of the first law. So we put it in different boxes, tied with a different ribbon. Energy of the isolated system is constant. This is not an isolated system, it's a closed system, but energy is changing energy of surroundings. All right, so we have delta U is integral along any path of du. So that's integral along any path of dq plus integral dw is equal to delta U. Well, there's so much repetition. That's one reason that it's so boring. Just keep saying the same thing over and over and over again. Somehow, some of us never manage to learn. I'm not saying that's true with you, but I know individuals who suffer from that condition. All right, so again, I said use a state variable, and all such variables, its derivatives, its derivative, like all others, state variables, is exact. Therefore, I repeat that. Regardless of the reaction path, Q and W are not state variables, and their derivatives are inexact. So we cannot say that the heat effect in the change in state up here is the integral of dq along the path and call it delta Q. We cannot do that. It is its integral, but it is not delta Q. And same thing, work is the integral along a specific path, and that is not delta W. Delta Q and delta W have no meaning in thermodynamics. We should never write it. Both of them have no meaning. Say that again. No, the integral of any state variable around a closed path, if you start at state one and go out on some excursion anywhere in the universe and come back to state one, then what's the integral of a state variable around that path? Must be zero. It's only over the starting state and the stopping state. So if you start in a state, go somewhere, and come back to that state, all the state variables are restored. It's just kind of like double talk. Does that make sense to anybody? All right. Now, mathematics has lots of symbolism, and one of my favorite symbols of mathematics is this integral sign for going around a circle or going around a closed path. So this means integrating around a closed path, any state variable of that integral is zero. And you can take that to the bank. Now, if the integral of du around the closed path is zero, then the integral of dq around the closed path plus the integral of dw around the closed path is zero because du is equal to dw. But individually, the integral around the closed path of dq is not zero, nor is the integral of dw around the closed path is zero. In general, they could be. Possibility that that'd be a very specific set of circumstances. In general, those integrals being inexact, integral around the closed path is not zero. But, and this is important, because this integral is generally not zero, and this is generally not zero. They are equal and opposite. You can take that back. This is our only chance, for generating a work flow from a heat in any kind of continuous fashion. That's what I say. The only way of generating useful work in the surroundings, which is minus W. I'm sorry about that. Historically, thermodynamics grew up with concern about taking a heat stream into some system that operates on a cycle and pouring out a workflow. And we're still concerned about that. And so naturally, they define the change energy of the system that it went as dq minus dw because it was working the surroundings of the choose. And now the Gooders came along sometime later and said we just had to fiddle with this vocabulary and change it all to having work done on all the system as possible, whereas work on the surroundings as possible. But there are these two definitions still exist in the literature. And so when you're going to literature, looking up thermodynamics, be sure to find out which version the most modern stuff will be, as I've printed here, dq plus dw is du. But, so that's why I say only chance to generate useful work in the surroundings minus W, that's useful work in the surroundings, to with a heat flow
with a heat to work converter, a Q to minus W converter, which we call a heat engine. The idea is to deliver heat flow on a cycle and produce usual work on a cycle in the surroundings, and then run the cycle over and over and over, and you've got heat coming in. And the trail, of course, is to maximize the efficiency of this conversion. Second law tells us how we do that, but this is some of the imagery I have. This is our system in here. It's operating on the cycle, and during the course of that cycle, it draws in heat from the surroundings, heat flow, except from the surroundings. It produces a work flow into the surroundings, minus W. And the natural way to define the efficiency of that is how much work is produced in a cycle divided by how much heat flows in. Now, this is what we want. However, to compare this, we have to scribble it out. So here's what we want.
Can you bring the paper down? Thank you.
Okay?
Yes.
See the difference? What we want is operate this heat engine on a cycle, and during the course of that cycle, take in a heat flow, except the heat flow from the surroundings at a higher temperature, of course. This would not go if the surroundings were hotter, higher temperature than that. Right? There's no mechanism for generating the heat flow other than a temperature difference. There's no mechanism. So if I draw it this way, then it's necessary that this comes from some temperature out here that is higher than the temperature right here in the system. And producing minus W, that's your work in the surroundings. That's what we want. What we always get is this. We operate this sucker on a cycle. We draw in some heat flow, Q, from, it's coming out here from, call it T1, which is higher than this temperature right there with that boundary. So the heat flow comes into the system, and you produce some work out minus W. As always, so minus Q. So that's Q1 in, minus Q2 out. That's some temperature T2 that's lower than Q1. That's what's false. Therefore, the efficiency of Q to minus W conversion, which is minus W divided by Q1, is less than 100%. We want 100%, it's got to be less. And this is the second law of this way, the rest of line tells us how much less. So I said before, that would be more interesting than this stuff. All right. Just mentioned here that any workflow can be converted 100% into a heat flow. Going this way, you don't need to worry about cycle or not. We've got work in, minus Q out. If we put in 1,000 joules here, we can easily, duck soup, get out 1,000 joules of heat. But not going the other way. The fundamental limits on the conversion of heat to work, heat flow to work. All right. Now, written out a number of things that you need to know about energy heat work. tea and have some hot coffee here. There's a couple of them in each of these, and the temperatures are widely different. So, everybody knows which one of those has more heating, right? Which one? Which one of those has more heat? Everybody knows that. But not everybody has read my notes here. No. Heat and work are not forms of energy or properties of matter. They're description only of energy and motion, those of heat and work. This is the hardest thing that I ever have to try to teach you. Hardest thing for you to learn, but I don't know why I really won't. But the answer is neither one of those has any heat in it. The core of the sun is very, very hot. How much heat's in there? None. Heat is not a physical property. That rubs against every fiber of your being because you want to think it is, because you've been told it is, taught it is, and that's absolutely wrong. And we've known about this for, 150 years, a long that time. All right, let me see if I can convince you. That stands for, that's not New Brunswick, but nota bene. In Latin that means pay attention. Period. I got a voice going down there somewhere. There's a spring. Now, I put this spring out here. I'm gonna take this steel off. Okay, let me pretend. I put the steel ball on it with backspin. How more work in it than it had before? Would be surprised if I told you it didn't have any work in it at all. You wouldn't know. So why the hell are you astonished when I tell you that you warm a cup of water up that doesn't have any heat in it? It has energy in it. Hot water has more energy than cold water. But it ain't got no heat. And a compressed spring has more energy than a relaxed spring, but doesn't have any work. That's easy enough to understand, isn't it? That's good. Get it? All right. So I'm telling you this. Let's just look at some demonstrations. We'll write down the changes. 1 cup of water. We specify enough about it for its state to be identified. So it's liquid. And it's initially at 25 degrees Celsius. At some pressure, we'll assume atmospheric pressure, and don't worry about it. And the change in state is to 1 cup of water. It's still liquid, but it's right at or near the boiling point. So it's 100 degrees Celsius. Do we have any way of knowing how much energy is required to bring about that transition? Sure, we know the heat capacity of water, we know the temperature change, and and that's pretty trivial. So I'll leave this in delta U form. Delta U here is equal to U2 minus U1, and it's about 63 kilojoules. Okay? So that's, you can determine that experimentally, and there's a thermodynamic equation. But the delta U has to be equal to Q plus W. And yes, Q plus W. All right. So tell me, what is W for this process?
Would it be 0?
All right. There's a little change in volume, but we're neglecting that. So it's 0. So what is Q? 63 kilojoules. That's very good. Okay, so this is path 1. How many paths are there going from room temperature water to -3 water? And infinity takes together. Okay? Continue closely to path 2. Path 2, here's what I'm going to do. No. I didn't even show you how to do path 1, I'm sorry. Here's the way we do path 1. It's a cup. There it is. And we put a flame under it. And that's the process I'm talking about. So you can see the heat flow into there. Sorry. So path 2, how are we going to do that? I'm going to take the cup, an insulated cup, and that has to be the same cup, same water, has to be the same amount of water. So we've got our water in here, and there's the level of water, and I put electrical resistance down in there, and pass a current through it. Called half. If I heat, should you say it? If I add energy to that water by running electricity through that wire, will it get hot? Absolutely. Absolutely. So I can carry out the same change as that. So let's write down for path 2, delta U2 is equal to Q2 plus W2. So what is W2? Well, it's got to be 63 kilojoules, does it not? That's our source of energy. So what is Q2? How much? Thank you. How much heat flowed to that water? 0.
Is this what you mean by when you say there's a million ways to get
Say
there?
again?
Is that what you mean by when you say there's a million ways to get there? So there's like a million different ways to
I said
heat up?
infinity of ways.
Oh, sorry, infinity different ways.
Yeah,
Is
not
that
a million.
okay?
There's
Okay.
a million to a million to a million to a million.
Yeah.
Right. And we don't have to write them all down. have we?
Yeah.
I'm going to write down 3 of them.
Okay.
So you say, well, yeah, no. See, this wire is down in the system. The boundary is the surface of the water. There's no heat going in from the surroundings. This ought to convince you that there's no damn heat in that water. There's energy in it. 63 kilojoules it didn't have before. All right, I'll look at a third way. There's an infinitude of ways of doing it. Just look at the first. I take my cup full of water and pop it in my microwave and run it for a minute and a half or whatever. And voila, water gets hot. Right? Everybody understand that? So here we have delta U3 is equal to Q3 plus W3 is equal to 63 kilojoules. Now tell me, what is Q3?
Don't they both play a part in it?
No. No. How much heat flows to this water from being exposed to higher temperature? None. What's the temperature of a microwave?
Temperature?
Light doesn't have a temperature. But it absorbs the light, which is a form of energy. And that is energy. And it absorbs energy and its temperature can go up. Right? This isn't magic. It's just everyday ordinary stuff. This is 0. So this is 63 kilojoules. How else could I do that? I could stir cold water with a spoon and stir in an insulated cup. Do it long enough, all that will get hot. How much heat flows to it? None. Where's it get the work? Works out of my body, getting to that doing the work about viscous forces, but all right, you still do this. Well, I mean, about this, I could come back here and I could have said that this work here is just equal to I squared R times length of time right here. That we know how to do electrical work. So what is this work here? This is just equal to the energy of a photon in a microwave times the number of photons and the energy of a photon is h nu of hc over lambda. And so the work is just equal to hc over lambda times the number of photons. These energies are all the same. One was a heat flow because put the damn flame under that cup and it said, "Look, I'm hot." And the heat walked through that boundary. Heat is an energy. See, we're all brainwashed about this. If I have time, I'll tell you a little story. It happens to be time we can tell. Okay, so you still don't believe that? Well, we're going to, you're surprised, really not me, I just keep in there and it's really not. This one's real, we will do this. I have a system here. You see that? That's a piece of wire. That's just a piece of wire. And my system is a little bit of this wire, a little section of it, you'll see momentarily. And I'm going to give it some energy. I'm going to use one of these magic sticks. It still works. I want you all to watch this now. I want you to see the change of state that takes place. You can't see it. You gotta see this because seeing is believing, right? Of course. Unless you're going to be a magician.
Believing is seeing.
Alright, take this thing. I want to see this wire. Oh, can you see that? Can anybody see that? Can any of you see what's happening?
Yep. Glowing.
It's hot. It's hotter now. Where's that energy coming from? It's the heat flow out of the flame. So what we would say? That delta E, when we broke that state, was the one I brought up, but it was glowing. The energy came in as a heat flow. Oh yeah. Now I'm going to carry out that same change of state using a different energy source. It's 9-volt battery. So I take this
Where'd that energy come from? Came out of the potential energy in this battery. It got converted to kinetic energy to electric current. It got dissipated, it got fertilized in the water. And again, the idea that heat and earth are not substances. They're not properties. They're just descriptions of energy in motion, thermodynamics. Well, I shouldn't do this. I know it. Maybe you will forgive me considering my past years. But the opportunity to point out why I can't be too upset with another troubles with this, even though it's so blatantly obvious. Well, I give you two examples. I think I told you once that when I used to be a real professor, time to time I teach general chemistry, and I teach it sometimes parallel courses where we all gave a communal examination. And those of us who were teaching had to get together and create the exams and had to agree on the problems, and these were all silly questions on multiple choice and true and false crap like that. Sort of like you had last Friday. Now, anyhow, I told you about the one question I maybe never accept about properties matter being related to structure. Well, very often I would want to put this question on about here's a cup of hot water, here's a cup of cold water, and which one has more heat? Never once over a span of more than 50 years, never once would my colleagues agree to that. Because the answer was neither has any heat. Never once would a faculty in this department agree to that. Well, that maybe there's something. But during the past year, I was asked to, first, let me say, I'm not a chromatographer at all, but I do work with chromatographers and do consult for companies that manufacture chromatography equipment, and I do get called off from time to time to offer opinions. So I was advised that there was a problem in the chromatography community relating to present trends to push the pressures of the systems higher and higher and higher, and the analyses of separations faster and faster and faster. And so they're shoving liquids at high pressure or supercritical fluid like carbon dioxide at extremely high pressure through packed columns, and then analyze the cuts that go through. Well, as they inject, you all know more about chromatography than I know. Anyhow, the higher the pressures they go to, the more thermal effects they have in this column. The columns heat up. So there were explanations in the literature for this, big, long-winded, hairy explanations for what causes what the mechanism this actually is. And I was asked to look at it and comment on it and maybe write up a little note about it. And I was very naive about it. I just did. Well, you're pushing the front end of the top of the column, that's state one. And it comes out the end of the column, that's state two. And it has a pressure, the temperature, and the density. In state one, it has a different pressure, temperature, and density, state two. figure out why that temperature is the way it is. That's from the things, which it did. Wrote just a few paragraphs, and it got tagged on to a paper that one of my chromatography friends was submitting. And lo and behold, the review came back. I've had some negative reviews. I mean, this was scathing. It was like, I can tell you, the imagery that was associated with my knowledge of science. And the inception of it, that is true. So, I started out, I just whipped this out and figured everybody was familiar with this thermodynamics. It's easy to understand. The party line is that you have to take the Navier-Stokes equations, which are big, hairy, tensor-based equations of fluid flow, and evaluate the fluid flowing through this packed bed, which is a very complicated path, so it's impossible kind of thing to do analytically. But that's, you push this liquid through that column, and naturally it's going to heat up because of friction. Called frictional heating. That's simple, that's what it's called, frictional heating. I said, well, there's no way that any heat flows into that column by pushing high pressure liquid through, assuming that the walls are insulated and vapor. No way. There's no heat flow there. The temperature rises due to some other cause. I knew exactly what that was. Tried to explain it. But I was shot down and saying disrespectful, and I was desecrating the integrity and nobility of Navier-Stokes, particularly Stokes. I wasn't wrong. So I rewrote it and put it in mathematical proof that thermodynamic conclusion and the conclusion derived from Navier-Stokes were identical. And it didn't involve any heat flow. Oh, it came down to me even harder than ever. I mean, it was merciless. One of these, I'm not supposed to know who the reviewers are, and I don't know who they are, but my friend, that's a close packed community. Those chromatographers are doing big time chromatography, and they all know one another. It assures me that one of these reviewers teaches physical chemistry in a university somewhere. No, that's not right. This is due to frictional heating. This is due to the fluid rubbing against these particles of column and warming them up. And it's not. That's not true. That's true. So, well, the upshot is, then I finally just had to sit down and write out a full-blown paper on it. And go through the proof that the two treatments are identical, and neither involves a heat flow, and then explain to them that like the theory tells us where the temperature rises from. You compress the molecules together. When you squeeze molecules together against the intellectual forces, if they're real cozy, if the attractive forces are the dominant ones, they like that. Ooh, it feels good, it feels good. The kinetic energies make them move around so they can't just collapse to the lowest energy state. Then if they expand, they're moving away from the situation where they were attracted to the neighbors. So their potential energy going up, and the kinetic energy has to come down, which is an insulated container. And it cools off. So sure enough, that in chromatography, if you push it through under those conditions, it comes out colder at the end and it cools off. But if, on the other hand, they're squeezed together really, really tightly, so the repulsive forces are dominant, they hate each other's guts. They say, I can't wait to get away from you. And then they begin to expand and thaw and become less dense. They do fly away from each other, they give each other a kick in the rear as they're going, so they fly away, they gain kinetic energy. As they go out, they get some potential.
gets hotter because of the internal energy that's stored by compressing this stuff, let it expand. Well, Henry, my point was that people don't believe this. They want to believe thermodynamics. They want to believe that heat is not a real substance. So I did manage to get a little jab in, which I enjoyed. But I won't tell you about it. Anyhow, paper got published. All's well. And there's some guys that are sucking their thumbs. And, remind me a little bit of poor Galileo. We talked about him the other day when he was under the Inquisition and had to recant, go before the board and say, I'm sorry that I said that the earth goes around the sun. So I'm getting some of that. All right, so that's why I don't get too upset with students who say, hey, that's nonsense. It's not nonsense, it's true thermodynamics. All physical chemists who study thermodynamics know or should know and understand this. It's just that we're so habituated to talking about heat as though it's something real that triple that. Hi. Excuse me, but now let's get back to our study. So we have EU is equal to dQ plus dW. So the measure EU, and to understand, I could be writing del du, we're talking about a whole change of state, but you've got to go along each little step of the way sometimes, so you can do a du, you can integrate it, you can get that. So to measure du, by measuring dQ and dW, certainly a way to do it. How to measure these? Well, first, consider Earth. That's part of what the parents tell me all the time. I'll talk about some varieties of Earth. We've already mentioned most of these. Displacement of Earth. That is, dW is a force moving through a distance. That's basic Newtonian physics. And we chemists don't come across this very often, that you engineers will, more often than we. And that's, suppose that we have something that is rotating, radius r. To keep it rotating requires a force to be applied to it tangentially at some radius, and dW is equal to the force at dx again. Instead of moving it now, we're spinning, and that's the force dx is equal to r d theta, and we can combine the force, the radius, we call it torque, temperature, and so that's the way we measure, you know, the automobile engine that talk about torque's an important thing in terms of horsepower, like chemistry usually stopping things around test tubes and beakers and the like, and not in the garage, revving up engines, so we don't do a lot. But there's always 3. Adaptation work. Well, we all know we have two masses, M1 and M2, that the force is equal to M1 times M2 over a constant, universal constant gravitation, times the square of the separation distance between them. And if one is the mass of the Earth, and one is just plain M, then you can put those in easily enough. But if we're near the surface of the Earth, R is about the surface of the Earth, and we have force that is equal to the mass of the Earth over C times the radius of the Earth squared times M. And this is gravitational constant times M. And the force the work is just equal to M. G, displacement is H. Well, we don't have to do gravitational work in space or on the surface of the Earth, the moon, or wherever. For work of elastic deformation, I take the rubber band and I stretch it out. That takes it, I push it through. Oh, I can't do it. And such as compressing the spring or stretching the rubber band. Here the work is equal to minus the Hooke's law constant times the displacement. And that's the forces that the work is force times displacement. So it's minus KHX dx, and the integral of that gives us the work associated with that back. And one more. Of course, chemists don't deal with torque very much. They do a lot of over concern frequently with electric effects, especially in battery technology and electrochemistry. Right? So we include this one here briefly. Fluid charge. I'll use a lowercase u for charge in electric field. So let's set up electric field. Here I have two conductor plates that are charged up somehow. So that one gets a negative charge, then a positive charge. And the field exists inside here. If this voltage generates that charge separation in the field, it is equal to the magnitude of voltage divided by the separation of the plates. Physics, you slop a charge in here. Charge say Q plus. If the force on it this direction, it's equal to the magnitude of charge times the field strength. And it's easy enough to see that that EW is just equal to EW is equal to Q times V over L voltage times X. And if you move through that whole, across that whole field, start here and move all the way over there, we have W electric is equal to just the charge times the voltage. And this, you can do the mesh analysis on this and show that it has dimensions of energy. And the sheet meters dimensions you have, great doing that. And that's why we talk about things like the electron volt that we mentioned. And there was the I squared RT for involved in current. Oh, that was a 6-1. Radiation work. I've already told you that EW due to radiation of given wavelength lambda is equal to hc over lambda times En lambda, or hu times En of u photons, and how that equals to that wavelength. Now we've talked about a variety of work effects, but there's one that requires a little more attention, a little closer look, because whereas these other things like absorbing light, making something spin, making something compress, like spring, stuff of that sort. This is very common in chemical practice. There's one that you just cannot get away from, generally. It's almost always with us. And that has to do with the system undergoing a change of state and its volume changes. It expands some, contracts some, against some pressure, like the atmospheric pressure. So if it expands, it has to push back the atmosphere, it has to do work on the surroundings. And therefore the work effect on the system is negative if it expands. And if it collapses and atmosphere or whatever else is pushed on it compresses it and it gets smaller in body, then work is done on that. And so I guess that's all. Most common effect in most, not all, applied chemistry is what we call expansion work. And we single that out. We call that work expansion, or it's derivative BW, work expansion. All other works, categorize W non-expansion, which is a lot to write. So this is my notation. I generally write this as WX. If I write WX, I mean all the work is not just due to pushing, changing line. So the system undergoes a change in state. Then, in general, it might get the heat flow from something that starts at temperature T1, something that starts at T2, T3, Tn, maybe an infinity of these. gravitational field. It might get some work due to some extent of rotation. It might get some work due to some radiation. And other things that we haven't talked about yet. And we might get some work from expansion. Of course, that also means work contraction. So that's a general. So we could write down the first law as dq is dq1, dq2, dq3, dq4, dq, and dw electric, dw gravity, dw rotation, dw radiation, dw expansion. Generally, these are all Wx, W expansion. Really, we would write dq is equal to dq plus dw is equal to dq plus dw expansion plus dwx. That's actual kind of notation and all that stuff. Usually we assume that dwx is 0. But implicitly, we know that if there's any other kind of work, it has to be studied. Okay? When we encounter that in this course, then we'll say, oh, we have some other work. We have some other work where we'll get that. Normally, that's where we are. So now we want to know what is work expansion. Here's a differential area, dA, on the surface of a boundary between the system down below it here and the surroundings up above it. We don't have to know anything about the shape of the system. We just have to know there's a boundary, and you pick out any element, spot on it you want, and focus your attention on it. It's exposed to some pressure, call it the applied pressure. And the pressure is the normal force divided by the area. At an equilibrium, the system's pushing back with an equal and opposite force pressure balance at equilibrium. But suppose that some work is done to compress the system a little bit. This ds moves down by an amount of dx. dA moves down by dx. We have dw expansion is equal to the work done on the system by the surroundings. And that is equal to the force times the distance. And the force is pretty clearly equal to the applied pressure times the area. We have dx. And A times dx is the area, is dx. Applied pressure is just the volume change of the system. Contribution volume change of that spot. No, that's not quite right. Why not? Because it's the negative of the volume change. The way I've drawn that, the system's been compressed, so this amount of volume has been taken out of the system. But the work is positive, so so we had to put a minus. And that's the result. Okay, thank you much. We have PW expansion. It is a minus D5 DV. Now we draw a box around that.
Because this one, we use all of the time. I will, work on this type